Okay, so let's talk about the steady state approximation in more detail. And this is an addition to the chapter 17E about the topic 12 on the kinetics. And we are still talking about A goes to intermediate, go to the products. Okay, so this is a case where A goes to intermediate, goes to the product. And this is the typical pictures where you're seeing this steady state approximation. So this is a reactant, which is a concentration A, the product P. So you are making a product at steady stream and the concentration is coming down, and you are seeing a little small rise, but eventually the concentration of intermediate in the reaction mixture is not a significant portion of here. So what's trying to show in this figure is A is bigger than intermediate under the good steady state approximation. So in order for this one word to happen, this is a case where Ka value is smaller than Kb. So what that means is A goes to intermediate, and that's a Ka value, but that's a small. Compare, this is a fast, which is a Kb, which equals to the product. So what in the visual sense, what this really means is the analogy of the traffic is much easier to understand. So there are slow, steady streams of cars. There's a small road, but now there's a superhighway and moving the car from intermediate city to the product city. So therefore, as soon as the car arrives slowly in the intermediate city, they are just gone, taking the highway and just turning to product. So therefore, not enough chance to accumulate intermediate, right? So that's the case. So it's better understanding that, okay, Kb value is bigger than Ka value. So therefore, the intermediate has a little chance, and so this is all related to here. The steady state approximation is known as here, okay, and that's steady state approximation. But once again, the idea here is the rate of disappearance is much bigger than rate of production for the interference, so that you can keep in this one to be essentially small, right? Compared to your intermediate product, compared to your reactant. And there's another equation that is going to be pretty useful and simple to derive. So the concentration change is 0, means that the intermediate concentration remains to be constant, just as shown up here. Right? It's going to be 0, but I know that this one is being intermediate is being produced from A by this reaction, and the disappearing by this reaction. So that gives a very good convenient new equation telling me that, okay, so at the steady state condition, Ka times A is Kb times I. So that's how what comes in and what goes away are being balanced out, and that gives essentially intermediate concentration is Ka Kb times an A, okay, which is the equation shown up here. So once again, in the case of when Kb is bigger, the rate where these things are going away, the rate of disappearance is bigger, and that means an I value is smaller than A value at the steady state. Okay, so do you remember that the previous lectures I have this question? So this is these are the two questions from the test bank that I can show it to you. That is about the steady state questions. Okay, these are the equations, the reaction. Okay, the consecutive reaction and the steady state. Okay, the steady state approximation is for the intermediate, right? So it's about the intermediate concentration. So A or C is the answer. And then we know that we want to essentially steady state approximation keep concentration low, right? So it means A goes to B, B goes to C, but you want this one to be faster so that there's not enough accumulation for the B. So that's a steady state approximation. What that means is K2 value here, K1 value here, K2 is bigger than K1. So that A is the right answer. Okay. The second one, this is what I showed before too, the steady state approximation for component B, and in that case, like I said, component B steady state approximation in the time, they shown a little bit, but eventually it is not a major factor. It's just that's a B concentration, whereas a concentration of A is non-zero value. That's where you have a reactant and it's decaying while keeping this A value is bigger than the value of the B at any time. So this is if you look at the differences, A is reactant concentration is bigger than your intermediate. Okay, that's the first constraint. And the second one is essentially the last one. Maybe I can use different colors. You start from 0 and then it kind of goes up, and that will be your product concentration. So that once again the K2 value is bigger than the K1 to have this steady state condition satisfied, where in the reaction mixture, if you're looking at any time, for example at this time, right, this is a concentration of product, reactant, and the intermediate is very, very small, and that's what the steady state approximation. So A is a correct answer to represent this idea. This is one of the kind of well-known example, and this is because of this is people study this one for, I guess, understanding the air pollution and so on, and so let's write it this one more time. The rate law of the decomposition of N2O5, and then we can write an equation just looks like that. So the net equation is 2N2O5 becomes 4NO2 and an oxygen molecule. Okay, and so this is essentially what is apparent reaction, and we are for this reaction is concerned, the decomposition N2O5 must be a certain reaction constant, and then from the experiment people find out N2O5 to the first power. This is a result. And remember, this is how we write. N2O5 goes to 4NO2 and O2. So these two colliding or something could happen, but why this is just first order, right? It's not a second order, it's a first order. So what that really means is this is a fact, this is an experimental observation that they find out this is the experiment result. But what this means is suggesting that this reaction is not elementary reaction. Right? It's not an elementary reaction. It is a complex reaction, and that's what it means. So we cannot just have a predicted knowledges. We just have to figure it out. And then people kind of postulate different kinds of intermediates in the product, and this is what they call the complex mechanism, and each one represented by the following mechanisms of elementary reactions. Okay, so those are elementary reactions. And then now let's just have a look at it, this equation for now. So this is a product, and then let me highlight what's okay. This is a product, and this is a reactant, and this is a product. So this is a reactant. Your product is NO2. Fine. So I'm just writing this one down. Okay, so then other than that, I am going to highlight something that is not reactant or product. So in here, I see NO3, and I also see NO, monoxide, and I guess a trioxide. So it appears here and there in these equations, and so on. So this is how we are going to understand this reaction now. This reaction is N2O5, right, becomes NO3, and eventually they becomes NO2, right? But as far as the concern, those are the intermediate, and then I am going to assume the steady state approximation, and for the intermediate that's shown up here. So this is what is shown up here. So these are the intermediate, NO and NO3, and their concentration is 0, and their concentration is 0. And then you, based on the notation shown up here, I'm just looking for NO, which is shown up here, and they're shown up here. So this is the one that being produced. This is the one that is disappearing. I guess from the third and the fourth reaction, right? So this is a third reaction and the fourth reaction. You can write it up. And as far as the NO3, this is more complex, being made, consumed, and you can put this one right away. And by doing so, you can solve this one for, and then you can have this expression to be made for NO3, and then you are going to put this the main equation, the first equation that as far as an N2O5 is concerned. Where's an N2O5? N2O5, this is our N2O5 is here. N2O5 is being made. N2O5 is being consumed. So those are the three reactions. So those are the three reactions that involve with production and the consumption of N2O5. That is essentially net reaction rate. And then finally, you get to you lead to the equation. Just looks like that. Okay. So this is a good example where now what is as a net result, you are seeing the first order reaction, right? So therefore, the decay of N2O5 is first order rate law, and then there's a combination of that. So that's how the people use to calculate. I mean, this is all the postulate, and of the elementary reactions, and using the steady state approximation, they calculate the concentration of how the intermediate concentration is related to your either product concentration or the reactant concentration and the product concentration, and also the NO, which is that's under the intermediate concentration, is also you can use that because this is already we know, so we can use this one to be here, and then you can calculate those two values. Once you know that, this value intermediate concentration, and so these values and this intermediate concentration values can be put that in, and then you will be leave nothing but just the first order reaction components being there. So once again, this complex reaction N2O5 is decaying into 4 NO2 with oxygen, is not elementary reaction. And there's it is a complex reaction. The net reaction rate law is essentially minus Kn2O5 to the first one. So the first order reaction is actually very complex story behind it, and that's how people find out is essentially a series of reactions, of elementary reactions that is responsible for that.